So moving on. So let's get into Raman spectroscopy. So I always like to really point out that this is not Raman or Ramin. For 10 years, I've been listening to students mispronounce this. So this technique is named after Chandrasekhara Raman, an Indian scientist. He won the Nobel Prize, so it's C.V. Raman. He was the first Asian to win the Nobel Prize in 1930. Pretty cool. And so he won this Nobel Prize for his descriptions of light scattering, particularly this notion of how we can use scattering as a form of spectroscopy. So let's describe this, because this is a very complicated effect. Okay? So it starts by bathing a molecule with incident EM radiation, right? And typically visible light is used to best drive this technique. And because light is an oscillating electromagnet, right? We know that there's little oscillating dipoles. When there's a really intense field of light bombarding a molecule, it can actually distort the electronic environment. Okay? So this shaded area that you're seeing are the MOs, the molecular orbitals, getting distorted from their resting, room temperature ground state configuration. Okay? So this light distorts the electromagnetic field. And as a result, it actually then scatters off of that electromagnetic field. And I've drawn this to look like a grating because, in fact, what happens in this technique, it's really like a molecular grating. Okay? So it doesn't quite work the same way as the grating equation where we consider the different indices of refraction. But all of the same, it's very similar to that in that it is a scattering technique. This is not an absorption technique. It's scattering. Okay? And so these are the rules for rotations. So we can have rotational Raman, or we can have vibrational Raman. So these are the quantum numbers for rotational, and I'll describe how that's different for vibrational. Okay? So for the J equals 0, so if there's no effect on the rotational state, we just call that Rayleigh scattering, and there's no effect. So if the incident radiation is coming in at, let's say, 532 nanometers, the Rayleigh scattered light will also come out at 532 nanometers. So, and the reason why I pick 532 nanometers is because that is a green laser light, which is typically used for the Raman effect. Okay, so that 532 nanometer green laser works universally quite well for most molecules. So the Rayleigh scattered light will also be 532 nanometers. Okay, and in fact, the Rayleigh light scattering effect is the description of why the sky is blue, right? There's very small molecules out there, and so the atmosphere is made up of very small molecules, particularly nitrogen. Nitrogen is the right size to scatter blue light quite effectively. Okay, so here we have white light coming in from the sun. And all of this light is scattered off, right? Rayleigh scattering. But the blue in particular is scattered the most effectively. Okay? So that's a simple description of why our sky is blue. And in fact, any other celestial object that has an atmosphere containing nitrogen will also be blue, right? Which is pretty cool. So now when the rotational levels are affected, the J, when it increases the rotational state, we call that the Stokes shift. And when it decreases the rotational state, we call that the anti-Stokes shift. Okay?